Welcome to another episode of Learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. In this video, we discuss the 11 questions that are given from Unit 1, that is sets, relations and functions. These 11 questions are related to sets and equivalence relations. Sets, different types of relations and equivalence relations. These 11 questions have appeared in the JEE Main examination held in the January 2025 session. So, we discuss these 11 questions and their solutions in detail. Right, this is the first question. And this question has appeared on 24th January 2025 in the morning shift. The given question is, let S is equal to the set consisting of P1, P2, etc. P10 be the set of first 10 prime numbers, that is prime numbers like 2, 3, 5, 7, 11, etc. Like that, the 10 prime numbers are there in S. Let A is equal to S union P, where P is the set of all possible products of distinct elements of S. What is P? P is the set of all possible products of distinct elements of S. Now, products of any two elements, products of any three elements, products of any 10 elements. So, all such things are in P. Then, the number of all ordered pairs, ordered pair x comma y, x belongs to S and y belongs to A, such that x divides y. Here the catch is x divides y. So we have to count the number of ordered pairs x comma y, where x belongs to S, the first component comes from S, and y, the second component, belongs to A. A is S union P. And we have to count the number, and the number is. Let's now discuss the solution of the problem in detail. We have S is equal to the set of the first 10 prime numbers P1, P2, etc. P10. Given P is the set of all possible products of distinct elements of S, and A is equal to S union P. We want to count the number of ordered pairs x comma y, where x belongs to S, y belongs to A. What is A? Is equal to S union P, such that x divides y. So, we continue in the next slide. Yes, we want to count the number of ordered pairs x comma y. First component x belongs to S, the second component y belongs to A, where A is S union P, such that X divides Y. Let X belongs to S, fix it. So that means we want to fix X and make an argument. Then afterwards, X belongs to S, therefore the same procedure we will extend to all the elements of S. There are 10 elements in S. So X belongs to S, fix it. Then we have case 1. X divides itself, because we have to count such ordered space X comma Y where X divides Y. X divides itself, so we count 1 for the pair X comma X. 2. Case 2. X divides any product in P that contains X. Now you take a product of 2 elements of S, and if your X divides, say, P1, P2, then X either divides P1 or X divides P2. That means this P1, P2, you have to take it as XP1 or XP2. Then only X divides any product in P that contains X. So, you take any product in P that contains X. That means it's a product of elements of S and one of the element is X. Then X divides obviously that product that contains X. Like X divides itself, we have already counted. So our count will be, that is, products like product of X multiplied by an element of S. Then X divides this one. Or X product of 3 elements that contains X. So these 2 elements, these 2 blanks are to be filled up with the elements of S. Product of 4 elements containing X. Then the 3 elements, these 3 blanks are to be filled with the elements of S. What are all possible ways of filling up these things? At the end, etc. At the end, so the product of 10 elements, one of the element is X. So you have to fill up these 9 places, 9 blanks with these elements of S. Now come to the first case. Product of 2 elements, one of them is X. Then you have to fill up this blank in how many ways? Out of the 10 elements, having selected X, we have the remaining 9 elements, because these are the products of distinct elements, therefore repetition is not allowed. Therefore, to fill up this place, we are left with, because X belongs to S, we are left with 9 elements. In how many ways you can fill up this one? 9C1. So the number of products containing X is, this one is 9C1. And the product of 3 elements containing X, these 2 blanks can be filled by, in how many ways? 9C2 ways. This one, 9C3 ways, etc. This one, 9C9 ways. So the number of products containing X is 9C1 plus 9C2 plus 9C3. This is a mistake. Plus, etc. plus 9C9. What we have done is add and subtract 9C0. Then these things 9C0, 9C1, 9C2, etc., 9C9 is the sum of the binomial coefficients. This is 2 power 9 minus 9C0 is 1. So this is 2 power 9 minus 1. And what is the total number of? Thus, the number of ordered pairs for a given x, I am stressing, for a given x, because x we taken from S and fix it, for a given x is 2 power 9 minus 1, and we have already counted 1, so plus 1, that is 2 power 9, and that is 512. This is true for one x belongs to S, and this we have to do for each x belongs to S, and S has 10 elements. Therefore, the required number of ordered pairs for all x belongs to S will be order of S multiplied by 512, that is 10 into 512, that is 5120. That's our answer. The answer is 5120. Yeah, this is a good question. Right. We move to the second question. This question has appeared on 22nd January 2025 in the second shift. It is on relations. Let A be the set consisting of the elements 1, 2, 3. The number of relations on A containing 1, 2, ordered pair 1, 2 and ordered pair 2, 3, which are reflexive and transitive but not symmetric is fill the blank. So, we have to count the number of relations on A containing these two ordered pairs which are reflexive and transitive but not symmetric. How many? That's the question. What is a relation on A? It is a subset of A cross A. Right. Let's now discuss the solution of the problem in detail. We have A is equal to the set consisting of 3 elements 1, 2, 3. Recall, a relation R on A is reflexive if the ordered pair A, A belongs to R for all A belongs to A. A relation R on A is symmetric if A, B belongs to R, then B, A belongs to R. A relation R on A is transitive if A, B belongs to R, B, C belongs to R, then the transitivity will tell you A, C also belongs to R. A relation R on A is a equivalence relation if it is reflexive, symmetric and transitive. Yes. Now, let R be a relation on A containing 1, 2 and 2, 3 which are reflexive and transitive but not symmetric. Let R be a relation on A containing 1, 2 and 2, 3 which is reflexive and transitive but not symmetric. This implies because it is reflexive, R must contain the set of ordered pairs 1, 1, comma 2, comma 2, comma 3, comma 3. Union, the set consisting of 1, comma 2, comma 2, comma 3, because it should contain 1, comma 2 and 2, comma 3. The first one is reflexivity, and this is the condition what is given to us. Now, since R is transitive, 1, comma 2 belongs to R, 2, comma 3 belongs to R. By transitivity, 1, comma 3 should be there in R. So we adjoin this 1, comma 3 to this. Now R1, let's call the relation is R1, is the set consisting of 1, 1, 2, 2, 3, 3 reflexivity, 1, 2, 2, 3, use the transitivity, you get 1, 3. Now let us see, transitivity is satisfied. Transitivity is satisfied. Now, what about symmetry? 1, 2 is there, 2, 1 is not there, 2, 3 is there, 3, 2 is not there, 1, 3 is there, 3, 1 is not there. Say yes, yes. It is reflexive, transitive, but not symmetric. Therefore, this is the relation with the given said properties. Now R1 is this one, is a relation. That means we are successful in getting the first relation with the said properties. Now look at R1. What are the remaining ordered pairs which are left out? That is, which are not included in the above relation. They are 2, comma 1, which is the symmetric form of 1, 2, 3, 2, 3, 1. Right. So we deal with 3 cases. Suppose we adjoin 3, comma 1 to R1. Then it becomes 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 1, 3. Transitivity has come. Now 3, comma 1 we have adjoined now. Right? Now, it is not transitive. Why? Why? Because 3, comma 1, 1, comma 2 will imply 3, comma 2. It is not there. It is not there. Right? Not only that, 2, 3 is there, 3, 1 is there, 2, 3, 3, 1 will imply 2, 1 must be there for transitivity. It's not there. That is why it is not transitive. Okay, what I will do is, I want to get a transitivity for this. We will adjoin to 1, because once I put 3, 1 and I want transitivity, you need 2, 1 and 3, 2. So we will adjoin that there. Then it results in R1 star is 1, 1, 2, 2, 3, 3, 1, 2, 2, 3, 1, 3, 3, 1, 2, 1, 3, 2. What is this? This is precisely A cross A, the whole of the all ordered pairs have come, and that is always an equivalence relation, that is reflexive, symmetric and transitive. But we are looking for what? We are looking for a reflexive relation which is transitive but should not be symmetric. Therefore, this is not a candidate for us. And this analysis will tell you that you cannot join 3, 1. So 3, 1 cannot be adjoined to that. So that 3, 1 is ruled out. Go to the case B. Case B. Suppose we adjoin 2, 1. So we have 3 elements here, 3 cases we deal with. 1 we have already done, 2, 1. Suppose we adjoin 2, 1 to R1. So then R2 is 1 1, 2 2, 3 3, 1 2, 2 3, 1 3, and now adjoin to 1. Now, what about transitivity? Transitivity 2 1, 1 1, 2 1, 2 1, 1 2, 2 2, 2 1, 1 3, 2 3. Is there? Is there? No problem. No problems will come. And transitivity is also achieved. And for 2 1, symmetric 1 2, then R2 is 1 comma 1, 2 comma 2, and 1 2 is there, 2 1, 2 1 is there, 1 2, symmetric has come for this ordered pair, not for all. 2 3 is there, 3 2 is not there, it's not symmetric. 1 3 is there, 3 1 is not there, it's not symmetric. But it is a relation which is reflexive, transitive, but not symmetric. So it's a relation with the said properties. Option C. Suppose we adjoin 3 2 to R1. Then we'll get R3. Now, again you will see 3 2 is there, 2 3 is there. That doesn't mean we have achieved symmetry. We have not achieved. It is there. We will achieve symmetry when for each one of them it's a reverse. When AB is there, BA should also be there for all AB. Whenever AB belongs to R, BA should belong to R. So 1 2 belongs to R, 2 1 belongs to R is not true. Therefore, it's not symmetric. So R3 is a relation which is reflexive, transitive, but not symmetric. This is a relation with the said properties. These are the only three possibilities. And thus we get three relations with the property as reflexive, transitive, but not symmetric. So the required number of relations on A is 3. The answer to this question is 3. That is the detailed discussion for this problem. Is also an easy problem. We go to the third problem. That is the last problem for this video. And this question has appeared on 29 January 2025 in the second shift. It's again on relations. Let S is equal to the set of natural numbers union 0. That is, N union, the singleton 0 means set of all non-negative numbers. Right. Non-negative integers. Right. S is equal to N union, the set consisting of 0. Define a relation R is an R from S to the set of real numbers R by R is equal to the relation all ordered pairs x comma y such that log y to the base e is equal to x times log of 2 by 5 to the base e, where x belongs to S and y belongs to R. Then the sum of all the elements in the range of R is equal to. We are given 4 options here. Let's now discuss the solution of the problem in detail. We have S is equal to the set of all natural numbers union the singleton set 0. That is the set of all non-negative integers, and R is a relation from S to the set of real numbers defined by are consisting of all those ordered pairs x comma y, where log y to the base e is equal to x times log of 2 by 5 to the base e, where x belongs to S, y belongs to R. Now let us see what is log y to the base e is equal to x times log of 2 by 5 to the base e, x belongs to S, y belongs to R, will imply log y to the base e is equal to log of 2 by 5 whole power x to the base e, implies y is equal to 2 by 5 to the power of x, where x belongs to S, where S is set of natural numbers union singleton 0. Let us recall the definition of the range of R. The range of R is equal to the set of all second components of the ordered pair x comma y. Ordered pair x comma y. Collect all the elements of the first components, then you will get the domain. Collect all the second components of the ordered pairs, you will get the range. So range is the set of all second components, that is y belongs to R, such that x comma y belongs to R, where x belongs to S. This is the set of all, what is y? 2 by 5 to the power of x, where x belongs to S. So for x is equal to 0, for x is equal to 1, for x is equal to 2, for x is equal to 3, like that, it is an infinite set. What is wanted? We want to find the sum of all elements in the range of R. In this range, these are the elements, the sum of all of them. The sum of the elements in the range of R is sigma 2 by 5 to the power of x, where the summation runs on x belongs to S. Take x is equal to 0. It is 2 by 5 to the power of 0, 1. X is 1, 2 by 5. X is 2, 2 by 5 whole square. X is 3, 2 by 5 whole cube, plus, etc. up to infinity. What is this? It is a geometric series with first term 1 and the common ratio 2 by 5, and the sum of up to infinity is given by a by the first term by 1 minus r, where r is the common ratio. That is equal to 1 by 1 minus 2 by 5, that is equal to 1 by 3 by 5, that is 5 by 3. 5 by 3. Thus, the sum of the elements in the range of R is 5 by 3. The answer, where is the answer in the options? Against option 4. The answer to this question is given in option 4. That is the detailed discussion of the solution of this problem, and it is a very simple and straightforward problem. Right. This is the fourth question. This question has appeared in the JEE Main held on 29th January 2025 in the morning shift. The question is related to relations. The given question is, define a relation R on the interval, it is a semi-closed interval 0 to pi by 2, closed at 0 and by x related to y by the relation R if and only if secant square x minus tan square y is equal to 1. Then R is, we are given 4 options. Option 1, an equivalence relation. Option 2, reflexive but neither symmetric nor transitive. Option 3, both reflexive and symmetric but not transitive. Option 4, both reflexive and transitive, but not symmetric. Let us now discuss the solution of the problem in detail. We have R, a relation on the semi-closed interval 0 to pi by 2, closed at 0 end, defined by x is related to y by the relation R if and only if secant square x minus tan square y is equal to 1. Let us now check one by one for reflexivity, symmetry, and transitivity of the relation R. First, we take y is equal to x. So that means we are going to check reflexivity. When y is equal to R, then x related to x if and only if secant square x minus tan square x is equal to 1. Wherever there is y, substitute x. X related to x by the relation R if and only if secant square x minus tan square y is equal to x, tan square x is equal to 1. Yes, this is an identity. This is true for all x belongs to the semi-closed interval 0 to pi by 2. That means x is related to x for all x belongs to the interval. Thus, the relation R is reflexive. Right. Now, let's go to the next slide for the discussion of the remaining two properties of the relation R. Second, x related to y. Our idea is x related to y implies y related to x. Is it so? If it is so, then it is symmetric. X related to y implies, by definition, secant square x minus tan square y is equal to 1 for all x belongs to the semi-closed interval 0 to pi by 2. This implies secant square x minus tan square y is equal to 1. That will imply, for secant square x we have written 1 plus tan square x minus, for tan square x we have written secant square y minus 1 in brackets. Right. Now simplifying, 1 cancels and you get a tan square x minus secant square y is equal to minus 1. No, there is 1 is not cancelling. Yeah. Minus of minus 1 is plus 1. 1 plus 1 is 2. That 2 when sent to the right hand side, 1 minus 2, that becomes minus 1. I'm sorry. Right. So now multiply throughout by minus 1. Then you'll get secant square y minus tan square x is equal to 1. It means y is related to x by the relation R. So x related to y implies y related to x. Then it will tell you your relation R is symmetric. Right. We go to the third property for the transitivity. X related to y and y related to z. If we can prove x related to z, then it is transitive. So x related to y means secant square x minus tan square y is equal to 1. Y related to z means secant square x minus tan square z is equal to 1. Right. So we will add these two things. So secant square x minus tan square y plus secant square y minus tan square z is equal to 2 on adding. For this secant square y, which is written in red, write 1 plus tan square y. Right. Tan square y cancels. And on the right hand side we have 2. Send this 1 to the other side, you will get 2 minus 1 is equal to 1. Then after simplification you will get a secant square x minus tan square z is equal to 1. This implies x related to z. So x related to z, whenever x related to y and y related to z, it means that the relation is transitive. Thus, our relation R is reflexive, symmetric and transitive. And any relation satisfying all these three properties is called an equivalence relation. Therefore, the relation R is an equivalence relation. Right. Let's look at our options. Our answer that it is an equivalence relation appears against option 1. Therefore, the answer to this question is option 1. That is the detailed discussion of the solution of this problem, and it is a very simple, straightforward question. Right. Let's move to the fifth question. This question has appeared in JEE Main 28th January 2025 exam in the morning shift. It's on relations. The given question is the relation R is the set of all ordered pairs x comma y, where x, y belongs to the set of integers z, and x plus y is even. And we are given four options. Option 1, reflexive and transitive but not symmetric. Option 2, reflexive and symmetric but not transitive. Option 3, symmetric and transitive but not reflexive. Option 4, an equivalence relation. Right. And it is a very, very easy question. And very rarely such questions occur in the JEE Main examination. Anyway, you are lucky to have a very simple question now. Now let's now discuss the solution of the problem in detail. We are given the relation R is the set of all ordered pairs x comma y, where x and y belongs to the set of integers z, and x plus y is even. Let us check the properties. 1. For any x belongs to z, for any integer x, x plus x is 2x is even. Whatever may be the x, but 2x will be even. That means the ordered pair x comma y belongs to R for all x belongs to z, thus R is reflexive. Second property. X comma y belongs to R implies x, y are integers and x plus y is even. When x plus y is even, y plus x is also even. So that will imply y comma x, the ordered pair, also belongs to R. So y comma x belongs to R whenever x comma y belongs to R. Therefore, R is symmetric. Option 3. X comma y belongs to ordered pair x comma y belongs to R, and y comma z belongs to R implies x, y, z are integers and x plus y is even because x comma y ordered pair belongs to R, and y plus z is even. This implies x plus y is even means 2 times some integer m, and y plus z is even means 2 times n for some integer n. Adding, you will get x plus y plus z, x plus 2y plus z is equal to 2 times m plus n. That will imply x plus z is equal to 2 times in brackets m plus n plus y, and m is an integer, n is an integer, y is an integer, m plus n plus y is an integer. 2 times of that is an even integer. So this implies x comma z belongs to R. So thus R is transitive. So R satisfies all the three properties: reflexivity, symmetric, and transitivity. Therefore, R is an equivalence relation. So let's look at our options. Options are given here, and the answer to this question is option 4. Right. That is the detailed discussion of the solution of this problem, and it is one of the most simplest questions that I have seen on relations in the JEE Main examinations. Anyway, you got a simple question. Be happy about it. Move to the next question, question number 6. This question has appeared in JEE Main examination held on 24th January 2025 in the second shift, and it is related to the sets, and it is precisely to find the number of elements in the union of two sets A and B. That is n of A union B you are required to find, and it's a good question. Let A is equal to the set of all x belongs to the open interval 0 to pi minus the singleton set consisting of pi by 2, such that log of mod sin x to the base 2 by pi plus log of mod cos x to the base 2 2 by pi is equal to 2, and B is the set of all x greater than or equal to 0 such that root x into, in brackets, root x minus 4 minus 3 times modulus of root x minus 2 mod is closed plus 6 is equal to 0. Then n of A union B is equal to. Right. It's a good question. Now we are given 4 options. Right. Now let's now discuss the solution of the problem in detail. We first take A. So A is here. A is here. So A is set of all x belongs to the open interval 0 to pi other than pi by 2. And log of mod sin x to the base 2 pi plus log of mod cos x to the base 2 pi, 2 by pi is equal to 2. First take this equation and solve for x. So this equation we have taken, and log of A plus log of B is equal to log of AB. That will imply log of mod of sin x multiplied by cos x to the base 2 by pi is equal to 2. Take over the log, you will get mod of sin x cos x, we have written 1 by 2 into sin 2x mod of is equal to 2 by pi to the power of 2, that is 2 by pi whole square. That is mod sin 2x is equal to 2 times 4 by pi square, that is 8 by pi square. And when you see what is this value 8 by pi square, it is approximately equal to 0.81. Yeah, this is worth noting. This is required. And this is less than 1 also, you don't know. And therefore A is the set of all x belongs to the open interval 0 to pi other than pi by 2 is such that mod sin 2x is equal to 8 by pi square. Right. And the easiest way is to draw mod sin 2x graph. This is the red one, is the mod sin 2x graph between 0 to pi. Pi by 2 is not included. Right. And as I have told you that 8 by pi square is approximately equal to 0.81, which is less than 1. Now draw a straight line parallel to x-axis, and the straight line is y is equal to 8 by pi square line you draw. It's less than 1, therefore it intersects. It intersects. Right. It intersects in how many points? 4 points. So therefore the number of solutions in 0 to pi other than pi by 2 is 4. Therefore, n of A is 4. This is the easiest way of getting the answer n of A is equal to 4. You have to note down 8 by pi square is approximately equal to 0.81, which is less than 1. And you have to note down mod sin 2x graph, modulus graph is this one only. Mod sin graph is this. And pi by 2 is not included. Agreed. The line y is equal to 8 by pi square parallel to x-axis. Because 8 by pi square is less than 1, it intersects in 4 points. 4 points in the interval 0 to pi other than pi by 2. Therefore, the values of x corresponding to these 4 points are the elements of A. Right. N of A is equal to 4. Right. And we move on to B. B is an algebraic equation. X, the set of all x greater than or equal to 0, such that root x into, in brackets, root x minus 4 minus 3 into bracket modulus of root x minus 2 plus 6 is equal to 0. Okay. We first solve this equation. Right. For this, put y is equal to root x in this. So this will imply y into y minus 4 minus 3 times modulus of y minus 2 plus 6 is equal to 0. Simplifying, y square minus 4y minus 3 times modulus of y minus 2 plus 6 is equal to 0. So because y minus 2 is under the mod, we have to deal with the two cases. One case is y minus 2 greater than or equal to 0. The second case is y minus 2 is negative. The first case, let y greater than 2. That means y minus 2 greater than or equal to 0. Then modulus of y minus 2 is y minus 2 only. Simply substitute here and solve. So y square minus 4y plus 3 times mod y minus 2 is y minus 2 plus 6. Simplify, you will get y square minus 7y plus 12 is equal to 0. And the factorization is very easy. Y minus 3 into y minus 4 is equal to 0. That implies y is equal to 3, 4. That is root x is equal to 3, 4. Squaring, you will get x is equal to 9, 16. Now you note down here itself 9 and 16, x is equal to 9 and 16 lie beyond this interval, because this interval is 0 to pi. 0 to pi. X belongs to 0 to pi other than pi by 2. When you take x is equal to 9, x is 0 to pi means 3.14, but it is 9. It lies outside. 16 also lies outside. That is the observation you make now. Case 2, when y less than 2, when y minus 2 less than 0, then y less than 2, then modulus of y minus 2 is 2 minus y. So wherever there is modulus of y minus 2, you write 2 minus y and simplify. Right. 3 into y minus 2. In that place, 3 into modulus of y minus 2. In that place, we have written 3 into 2 minus y. Here, it should be a modulus. Right. So, when you simplify, you will get y square minus y is equal to 0. That implies y into y minus 1 is equal to 0. Y is 0 and 1. That is root x is equal to 0, 1. Squaring x is equal to 0, 1. And you also note down that 0 doesn't belong to A, because it is the open interval 0 to pi where 0 is not included. So x is equal to 0 is not there in A. It only should talk about 1, whether it is in A or not. So what are you trying to say? What are 9 and 16 and 0 to 1? That is B. B is the set consisting of 0, 1, 9, 16. Those are the solutions. So n of B is 4. And in this we have already noticed 0, 9, 16 doesn't belong to A. Only the question is whether it belongs to A or not. That means what are you trying to say? How many elements are there common to A and B? That we discuss in the next slide. Right. We have A, we have B. Claim. Our claim is A intersection B is empty. That means there is no element common between A and B. So clearly 0, 9, 16 doesn't belong to A, because 0 is not in this interval, union of these two intervals 0 to pi other than pi by 2. 0 is not there by definition. And you also note down 9 is greater than pi, 16 is greater than pi. So 9 and 16 also doesn't belong to A, because in this interval they lie beyond 0 to pi. So it's only the question is whether one belongs to A or not. What are we trying to say is, what are the common elements between A and B? Assume that one belongs to A. I thought this is the only possible argument that we can put forth here. This implies 1 belongs to A means it should satisfy mod of sine 2 into 1 is 8 by pi square. Modulus of sine 2 is sine 2 only. Sine 2 is 8 by pi square. 8 by pi square. Now, sine 2 is measured in radians. Sine 2 is 0.91. 8 by pi square, we have already seen it is approximately equal to 0.81. If you say 1 belongs to A, sine 2 must be equal to 8 by pi square. It means 0.91 is equal to 0.81, a contradiction. Therefore, 1 doesn't belong to A. So there's there is no element common between A and B. A intersection B is empty. A and B are disjoint. Then n of A and B is equal to n of A plus n of B. Because they are disjoint, it's only n of A plus n of B. That is 4 plus 4, that is 8. Look at our options. Our answer 8 appears against option 3. The answer to this question is option 3. So that is the detailed discussion of this question, and this question is a good question. Right. This is the question that appeared in 23rd January 2025 in the second shift, and it is related to relations. Let capital X is equal to R cross R, where R is the set of real numbers. Define a relation R, capital R, on X as the ordered pair A1, B1 related to by the relation R to A2, B2 if and only if their second components are equal. That is, if and only if B1 is equal to B2. We are given two statements. Statement 1, R is an equivalence relation. Statement 2, for some A, B belongs to X, that means for some given A, B belongs to X, the set S is equal to the set of all ordered pairs X, Y from capital X such that X, Y related to the A, B represents a line parallel to Y is equal to X. In the light of the above statements, choose the correct answer from the options given below. We are given 4 options. Option 1, statement 1 is true and statement 2 is false. Option 2, statement 1 is false but statement 2 is true. Option 3, both statements 1 and statement 2 are false and both are true. Right. Let's now discuss the solution of the problem in detail. We have X is R cross R, the Cartesian product of R with R. So the set of all ordered pairs coming from X, Y, coming from X belongs to R, Y belongs to R. That is capital X, where capital R is the set of real numbers. And it is given a relation R on X defined as A1, B1 related to A2, B2 if and only if their second components, that is B1 is equal to B2. Right. We are now checking the properties of this relation R. Is it reflexive? For that, consider first, for each A1, B1 belongs to X, we have A1, B1 related to itself because their second components are equal. B1 is equal to B1. Thus, A1, B1 related to A1, B1 for all A1, B1 belongs to X. Thus, the relation R is reflexive. Let's see its symmetry. Is it symmetric? A1, B1 related to A2, B2 implies their second components B1 is equal to B2. B1 is equal to B2 implies B2 is equal to B1. Therefore, A2, B2 related to A1, B1. So, whenever A1, B1 related to A2, B2, we have A2, B2 related to A1, B1. Thus, the relation R is symmetric. Go for the transitivity. So, A1, B1 related to A2, B2 and A2, B2 related to A3, B3 implies from the first B1 is equal to B2. From the second, you will get B2 is equal to B3. This implies B1 is equal to B3. That means the first ordered pair A1, B1 related to A3, B3 because B1 is equal to B3. We are using the both ways of this if and only if. both ways of this if and only if. This implies the relation R is transitive. Thus, the relation R is reflexive, symmetric and transitive. Therefore, R is an equivalence relation. Agreed. Therefore, the statement 1 is true. Right. We move to the next slide for the discussion of statement 2. Right. Statement 1 is true. And the statement 2 says, for some A comma B ordered pair belongs to X, the set S consisting of all ordered pairs X comma Y belongs to X, satisfying X comma Y related to A comma B represents a line parallel to Y is equal to X. Is it so? Now let us discuss that. Now given for some A comma B ordered pair belongs to X, we have the set S is equal to the set of all ordered pairs X comma Y belongs to capital X, satisfying X comma Y related to A comma B. Now use the definition. The set of all ordered pairs X comma Y belongs to X. X comma Y related to A comma B means the second components must be equal, Y is equal to B. That is, the set of all ordered pairs X comma Y such that X belongs to R, Y is equal to B. It is the set of the ordered pairs X comma B, Y is B, where X belongs to R. So what are these? What are these X comma B? X belongs to R. As X is varying, B remains the same. What is this? It is a line. It's a line parallel to x-axis given by the equation y is equal to b. So it represents a line y is equal to b parallel to x-axis. But in statement 2 it is given it is parallel to y is equal to x. Therefore statement 2 is not true. So thus what we have shown, statement 1 is true and statement 2 is not true. Let's look at our options. And our answer tallies with option 1. Therefore, the answer to this question is option 1. That is the detailed discussion of the solution of this problem. This problem is pretty easy one. We move to the next slide for the next question. This is the 8th question. This question has appeared on 23rd January 2025 in the second shift. It is related to the concepts of sets. The given question is, let A is equal to the set of all ordered pairs x comma y belongs to R cross R, satisfying mod of x plus y greater than or equal to 3, and B is the set of all ordered pairs x comma y belongs to R cross R, satisfying mod x plus mod y less than or equal to 3. If C is the set of those ordered pairs x comma y belonging to A intersection B, satisfying x is equal to 0 or y is equal to 0. Right. And then sigma of mod of x plus y, where the ordered pairs x comma y belongs to C. That means sigma mod of x plus y, where this sigma summation runs on those ordered pairs x comma y belongs to C, is, we are given 4 options. And if you want to answer this question without using the geometry, it will be very extremely difficult. But whereas if you use the geometric ideas, that is what are these and all that, geometrically seeing, it becomes easier. So I will go in that approach. Right. Solution. First we consider we have B. set B. Set B is the set of all ordered pairs x comma y belongs to R cross R, mod x plus mod y less than or equal to 3. And this mod x plus mod y less than or equal to 3 is to be broken. You break this into 4 situations where x is positive, both x and y are positive, x positive, y negative, x negative, y positive, and both x and y negative. These are the 4 possibilities you can consider. So, option, we take the first possibility. X positive, y positive. Consider the line equality, x plus y is equal to 3. Let's call it as L1. What is this one? It is a straight line through 0, 3 and 3, 0. So these are the points of intersection of this line with the coordinate axis. Right. So this is the two-dimensional plane and this is the line L1. Right? Passing through 0, 3, 3, 0. But we have to consider this inequality. Now, x plus y less than or equal to 3 consists of all points on L1, y on because equal to, and below the line L1 because it is less than. Is it below or above? How do we decide? So what you do is you take a convenient point. The most convenient point for us is 0, 0. Substitute in this. 0 plus 0, that is 0 less than or equal to 3. It is satisfied. Therefore, it represents the region in which this 0, 0 is present. That means in this. Below the line L1. All this. Right. Go to x positive, x negative, y positive. Then L2 will be minus x plus y is equal to 3. What is it? It is a line through 0, 3 and minus 3, 0. Right. So this is the line. And we have to consider the inequality. So minus x plus y less than or equal to 3 consists of all points on L2. Yes, because it is included, is equal to is included. And below the line L2. Why below? Take the convenient point 0, 0. Substitute in this. It is satisfied. Therefore, this represents that region in which 0, 0 is present. So, it is the below. Right. Go to the third case. Now, x positive, y negative. So, L3 is x minus y is equal to 3. What is it? It is a line through 0, minus 3 and 3, 0. Now consider inequality. So this is the line. And 0, minus 3 is here. 3, 0 is here. Consider the inequality. X minus y is less than or equal to 0. Consists of all points on L3 on the line above the line L3. Again 0, 0. Substitute in this. It is satisfied in this inequality. So it represents that region in which 0, 0 is present. That is above the line L3. Similarly, fourth case, x is negative, y is negative, L4 is minus x minus y is equal to 3. It is a line through 0, minus 3 and minus 3, 0. So this is the line. So these are the points. Right. And consider the inequality. Minus x minus y is less than or equal to 3 consists of all points on L4 and above the line L4. Agreed. Now, this is the union of all these things. The union of all these and, not union, I am sorry. And. So, and means intersection. So, therefore, what is B? B is the set of all points that lie inside and on the square with vertices 3, 0, 0, 3, minus 3, 0, and 0, minus 3. How do you get this? This is by taking the intersection of all those 4 regions. So this is the set of all points that lie inside and on the square, on because equalities are there, inequalities are there. So it's the square with vertices at 3, 0, 0, 3, minus 3, 0, and 0, minus 3. Right. So the B, capital B we got, and we have to go to capital A and take its intersection. Right. Right. So we have B, and what is B also? We have represented B here, and B is the set of all points that lie inside and on the square with vertices, this as shown here. We have A, the set of all ordered pairs belongs to R cross R such that mod of x plus y greater than or equal to 3. We consider two cases where x plus y is positive, where x plus y is negative. So that way we will write it as A1 union A2. Right? So for the x plus y positive A1, x plus y is negative A2. So where A1 is set of all ordered pairs x comma y belongs to R cross R such that x plus y greater than or equal to 3, where x plus y is positive. So what is this? What is this? At one stretch I will talk about this. I'll talk about this one. So A1 represents what? A1 represents the set of all points that lie on this line, x plus y is equal to 3, and above, all points that lie above this line. So A1 consists of all points on L1, x plus y is equal to 3, and above the line L1. Why this above the line? Why this above the line? Now take your convenient point 0, 0, substitute in this. 0 greater than or equal to 3 doesn't satisfy. Therefore, the region, this region A1, is that region in which 0, 0 is not present. That means it is the line and above it. So right, what is A2? A2 is set of all those ordered pairs x comma y belongs to R cross R minus x minus y greater than or equal to 3. It is the situation when x plus y is negative. Right. Right. So what is this? A2 consists of all points on L4. This is the L4. Minus x minus y is equal to 3. And below the line L4. So this is the below the line. Now first of all, you take A1 and intersect with B. So B is this one. A1, all points are on this line and above. If you take the intersection of A1 with B, it is this line segment joining 0, 3 to 3, 0. And you take A2, A2 is this region, intersect with B, then you get the line segment joining minus 3, 0 to 0, minus 3. Now we consider A intersection B. A is A1 union A2 intersection B. Use the distributive law A1 intersection B union A2 intersection B. And what is A1? All points on this line and the points above the line, intersection with B, it is the line segment joining 0, 3 to 3, 0. That is the set of all ordered pairs x, y, where y is equal to 3 minus x, where x varies from 0 to 3. This is A1 intersection B. Right. What is A2 intersection B? A2 is this region those points lying on this line and the below this line intersection with B is this line segment joining minus 3 comma 0 to 0 comma minus 3. That is the set of all ordered pairs x comma y is equal to minus 3, y is equal to minus 3 minus x, where x varies from minus 3 to 0, including minus 3 and 0. So, now given C is the set of all those ordered pairs x comma y belongs to A intersection B, such that x is equal to 0, y is equal to 0. So, on this line segment, you have to consider those ordered pairs for which either x is 0 or y is 0. What are those ordered pairs? For x is equal to 0 or y is equal to 0, 0 comma 3 or 3 comma 0. And what are those ordered pairs on this for which x is 0 or y is equal to 0? They are minus 3 comma 0, 0 comma minus 3. So, C consists of only these 4 points. And C is the set of all those ordered pairs 0 comma 3, minus 3 comma 0, 0 comma minus 3, minus 3 comma 0. So, now you have to find sigma mod of x plus y, where the sigma runs on those ordered pairs x comma y which belong to C. That is mod of 0 plus 3 plus mod of 3 plus 0 plus mod of 0 plus minus 3 plus mod of minus 3 plus 0. That is 3 plus 3 plus 3 plus 3 4 times, that is 12. Let's look at our options. Our answer 12 appears against option 2. Therefore, the answer to this question is option 2. Right. That is the detailed discussion of this question. As I have already mentioned you in the beginning of the question, this question is to be seen geometrically. Then it becomes easier. Otherwise, it will be difficult. Question number 9. This question has appeared in the JEE Main 23rd January 2025 in the morning shift. It is related to equivalence relations. The given question is, let R is equal to the set consisting of 3 ordered pairs 1 comma 2, 2 comma 3, 3 comma 3 be a relation defined on the set consisting of 4 elements 1, 2, 3, 4. Then the minimum number of elements, that is the minimum number of ordered pairs needed to be added in R so that R becomes an equivalence relation is, we are given 4 options. Right, it is a very simple question. Let's now discuss the solution of the problem in detail. We are given S. Let S be the set consisting of the elements 1, 2, 3, 4. We are given R is a relation on S, where R is given as ordered pairs 1 comma 2, 2 comma 3, 3 comma 3. It's a relation on S. Agreed. Now, then the minimum number of elements needed to be adjoined to R so that R becomes reflexive. First of all, we take this R. Is this R an equivalence relation? No. So, to make this R an equivalence relation, we will adjoin those elements, those ordered pairs to R so that this R, when added those elements, becomes reflexive. So, in R, we only have 3 comma 3. To make it reflexive, we need A comma A belongs to R. For all A belongs to S. So we have to add, we have to adjoin 1, 1, 2, 2, 4, 4 and 3, 3 is anyway there in R. So we have to adjoin 3 ordered pairs so that R becomes reflexive. Then the resulting R, we call it as R prime. Let R prime be, after adjoinment, 1, 1, 2, 2, 4, 2. These are the elements which we have adjoined. And 1, 2, 2, 3, 2, 3, 3 is already there. Now the question is it an equivalence relation? No. Why? Because symmetric property is not satisfied. And you need not check for this ordered pair, say, A, the symmetric property. It is already there. So 1, 2 belongs to R prime, but 2, 1 is not there in R prime because the symmetric nature is not there. 2, 3 is there in R prime, but 3, 2 is not there. So to make it symmetric, we will adjoin this 2, 1, the minimum number of elements needed to be adjoined to R prime, so that R prime becomes symmetric, or 2, 1, 3, 2. So 2 ordered pairs we will be adding. Now you adjoin, then the resulting relation is R double prime is equal to 1, 1, 2, 2, 4, 4, 1, 2, 2, 3, 3, 3, 3. And these are the 2 elements which we have added, 2, 1, 3, 2. Now look at this R double prime. Is it transitive? Is it transitive? Now see, 1, 2 belongs to R double prime, 2, 3 belongs to R double prime, and to be transitive, 1, 2, 2, 3 when composed, you will get 1, 3. Is 1, 3 in this? No. So we have to adjoin that element. But you want an equivalence relation, it should also be symmetric. When you adjoin 1, 3, 3, 1 also you have to adjoin. And look for the transitivity again. 1, 2, 2, 3, 1, 3, and the symmetric is 3, 3, 1. And any other. See, so the minimum number of elements needed to be adjoined to R double prime so that R double prime becomes transitive and symmetric, both. 1, 3, 3, 1. 2 ordered pairs you have to add. So after the adjoinment, this becomes R star. R star is set of all those. Now the adjoined ones is 1, 3, 3, 1. So now it is an equivalence relation. You can check reflexivity and symmetric. Symmetry is also there, and transitivity is also there in this. Therefore, thus it is an equivalence relation. So it may be checked that R star is an equivalence relation on S. Right. How many elements we have adjoined? Ordered pairs we have adjoined 3 plus 2 plus 2, 7. So the minimum number of elements, that is the ordered pairs, needed to be adjoined to R so that R becomes an equivalence relation is 7. 7 elements, 7 ordered pairs are the minimum number of ordered pairs to be adjoined to R so that R becomes an equivalence relation. So let's look at the options. Our answer 7 appears against option 1. Therefore, the answer to this question is option 1. That is the detailed discussion of the solution of this problem. It is definitely an easy problem. Move to the next question, question number 10. This question has appeared on 22nd January 2025 in the morning shift exam, and it is related to sets. Let A be the set consisting of 1, 2, 3 up to 10, and B is the set consisting of m by n where m and n belongs to A, m less than n, and the GCD of m comma n is 1. Right? So then the order of B, number of elements present in B is equal to, we are given 4 options. Agreed. Now, let's now discuss the solution of the problem in detail. Right. Now, given A, the set consisting of 1, 2, 3 up to 10. And we want to find the number of elements present in B, where B is the set of all m by n, where m and n belongs to A, m less than n, and the GCD of m comma n, that means is equal to 1. That means m and n are relatively prime. Agreed. For this, we have brought you a table here. Now, we first of all consider n. N, what is n in B? N is sitting in the denominator. So, if you take n is equal to 1, what are all those elements of A? Less than 1, no elements. Therefore, n is equal to 1 is not considered. So, now n is equal to 2. So, what are all those elements? Less than 2 in A is only 1. And out of these m's, now how many of them are relatively prime to n? So, GCD of 2 and 1 is 1. So what are the elements? Less than n, which are relatively prime to n? It's only 1. This one. Now, in B, the quotients are there, m by n. So, m is 1 by 2. So, how many number of m by n are there? 1 only. So, it's practically the number what you get here, you will be getting here m by n. Now, n is equal to 3. So, what are those elements in A? Less than 3, 1 comma 2. Now, what are those elements which are relatively prime to 3, which are less than n, less than 3? 3 comma 1 is 1, 3 comma 2 is 1. So, 1 qualifies, 2 qualifies, 1 comma 2. So, now m by n, m is 1 by 3, m is 2 by 3. How many? 2. So, the number of m by n is 2. 4. All the elements in A less than 4, 1, 2, 3. Now, what are the elements which are relatively prime? 4 comma 1, GCD of 4 and 1 is 1. 4 and 2 is not 1, therefore 2 is not considered here. And GCD of 4 and 3 is 1, therefore 3 qualifies. How many elements? 2 elements. What are the quotients? The quotients are 1 by 4, 3 by 4. How many? 2. So now go to 5. Elements of A less than 5. 1, 2, 3, 4. And 5 being a prime number, 5 is relatively prime to each one of these elements. So 5 comma 1 is 1, 5 comma 2 is 1, 5 comma 3 is 1, 5 comma 4 is 1. So all of them will qualify. So now how many m's? 1, 2, 3, 4. 4 elements, therefore 4. So the quotients are 1 by 5, 2 by 5, 3 by 5, 4 by 5. They are 4 in number. 6. Next n is 6. The elements of A which are less than 6 are 1, 2, 3, 4, 5. 6 comma 1 is 1, so 1 is qualified. 6 comma 2 is 2, is not qualified. 6 comma 3 is not qualified. 6 comma 4 is 2, not qualified. 6 comma 5 is qualified. GCD is 1. So 1 comma 5 only. So the number of m by n is 2. 7. So elements of A which are less than 7 are 1, 2, 3, 4, 5, 6. And 7 being a prime, every element is relatively prime to 7. So the GCD of m comma n is 1. Who are the m's? All these 1, 2, 3, 4, 5, 6. And the m by n's number is 6. Next 8. And elements of A which are less than 8 is 1, 2, 3, 4, 5, 6, 7. And what are those elements which are relatively prime with 8 out of these is 1, 3, 5, 7. They are 4 in number. The number of m by n will be 4. N is 9. We get 1, 2, 3, 4, 6, 7, 8. And in this 9 comma 3 is 3. They are not relatively prime. 9 comma 6, the GCD is 3. They are not relatively prime. Therefore, the remaining 1, 2, 4, 5, 7, 8. Right. How many? These are 6. So, lastly, we go to n is equal to 10. And what are those elements which are of A, which are less than 10? 1, 2, 3 up to 9. And what are the elements which are relatively prime with 10? 10, comma 2 is not. 10, comma 4 is not. 10, comma 5 is not. 10, comma 6 is not. 10, comma 8 is not. So, the remaining are 1, 3, 7, 9. How many? 4. So, thus, the number of m by n are given by the sum of these numbers. So, the total, so we get the total number is when you add all these, you get 31. So the number of elements in B is given by 31. Let's look at our options. Our answer 31 appears against option 2. Therefore, the answer to this question is option 2. That is the detailed discussion of the solution of this problem. Move to the last question, question number 11. Right. This question has appeared in the JEE Main exam held on 22nd January 2025 in the morning shift. It is related to, again, on equivalence relations. The given question is the number of non-empty equivalence relations on the set consisting of 1, 2, 3 is options. 4 options are given here, and these are the 4 options. Right. So, let's now discuss the solution of the problem in detail. Let A be the set consisting of 1, 2, 3. Right. And to find the number of equivalence relations on A. And since every equivalence relation R on A is reflexive, reflexive means A comma, the ordered pair A comma A belongs to R for all A belongs to A. So, in R, there should be 1 comma 1, 2 comma 2, 3 comma 3. Let R1 be 1 comma 1, 2 comma 2, 3 comma 3. It is reflexive. Is it symmetric? Yes. 1 1, 1 1, 2 2, 2 2, 3 3, 3 3. Is it transitive? Yes. Yes. So, here many of our students ask the question, sir, how to test transitivity here? Read the definition of transitivity. What the definition of the transitivity says? Whenever A comma B and B comma C belongs to R, then A comma C belongs to R. Read carefully. Whenever. So, is there a comma B and B comma C in R1? No. When there are no such elements, there is no question of the transitivity coming into the picture. Therefore, transitivity is not failed. Therefore, transitivity is satisfied. Right. It has a reflexive, symmetric and transitive. Thus R1 is an equivalence relation. So thus we got a first equivalence relation in that. So as we did in the earlier question, now to this set, to this R1, we adjoin some elements so that it becomes reflexive. It becomes an equivalence relation. Now let R2 be, we adjoin two elements, 1, 2. Because we have adjoined 1, 2, we want symmetric, 2, 1 also will adjoin. Now test for transitivity. Test for transitivity is again I tell you, whenever A comma B and B comma C belongs to R, then A comma C belongs to R. So transitivity is also satisfied. So it is an equivalence relation on A. In a similar fashion, go to R1 and adjoin in this similar form 1, 2, after 1, 2, 1, 3. If you add 1, 3, add also 3, 1. So let R3 is all those reflexive elements 1, 3, 3, 1. It's also reflexive, symmetric and transitive. In a similar fashion, next one 2, 3 and 3, 2 is also to be added. So R3 is an equivalence relation. R4, in the case of R4, 2, 3, 3, 2 and R4 is also an equivalence relation. That's all. So adjoining one element and its symmetric element results in equivalence relations like this. So basically you have that reflexive elements are there, to them we are adding. Now suppose you add 1, 2 and you want to 1, 1, 3 also, 1, 3 also. Then it becomes the whole set A cross A, A cross A. So let R5 is equal to A cross A, that is 9 elements you have to write. So these are the 9 elements of the ordered pairs. A cross A means the Cartesian product of A with itself. A has 3 elements. A cross A will have 9 elements. These are the 9 elements we have written. And it is the whole A cross A, and the whole A cross A is always reflexive, symmetric and transitive. Therefore, it is an equivalence relation. R5 is an equivalence relation on A. Right. Thus, we have obtained 5 equivalence relations on A. Therefore, the number of equivalence relations on A is 5. So, the answer to this question is option 1. It's not option 5. Option 5 is not anywhere there. The answer is 5. Option is 5. The answer is option 1. And in option 1, we have 5. The 5 we have written by mistake. Right. That is the detailed discussion of the solution of this problem. Now, it is worth mentioning here, is there, this is not for IIT JEE Main students, and those of you who are going for the advanced, they can think of how many equivalence relations are there on a given set A consisting of n elements. For 3, 5. For 4, how many? For 5, that means for 5 means for the number of elements are 5, how many? And there are methods of doing it. And please prepare such a kind of notes on order 3, order 4, order 5. There is a method of doing it also. This is a very elementary method what I have shown you, and that is worth making a notes on the number of equivalence relations on the set consisting of 3, 4, 5. That will be interesting and that will be useful to you. I am sure that you have understood all these 11 questions. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We certainly meet you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.